We're going to get started now. So for everyone that's joined us, thank you for your patience after last week. Whether you're a CyrusTree user or not, we do hope you find this interesting and helpful. We have over 200 people signed up for this, so we've asked that everybody keep their mic on mute for the duration, and we'll address all the questions. We may not address them all during this time period, but we will email you after the fact if that's the case.
Gracias por compartir, ¿oíste?
Please
Oye,
mute.
aquí estamos. Ay, marica, soy. Voy a tratar de conectarme de una.
Can you please mute?
Ya he visto las fichas.
Okay. As I said, keep your microphones on mute. We'll address all of your questions, some during this meeting, some will be directly after. And what else was I going to say to you? Oh, please put all of your questions into the chat, and we're going to be monitoring those. And as again, I said, we'll address those. I'd like to introduce Dr. Bunce to you. He built his first photosynthesis system 48 years ago as a graduate student and has been performing leaf gas exchange and many ACi curves ever since. He recently retired from the USDA ARS down in Beltsville, Maryland, and he was an environmental plant physiologist, and his current work involves predicting the impact of global change on plant physiology. He's used many brands of portable photosynthesis systems over the years, and he's quite partial to the Cyrus systems. In fact, he's been working closely with us in his retirement, developing in the development of rapid ACi analysis with our CyrusTree. He's recently published 2 articles that I've listed in the chat. They'll also be listed in our follow-up email for you if you'd like to read those. And I guess we'll just let Jim get started.
Okay, welcome everybody. So we're going to talk about the what, why, and how of ACi. First of all, what? A stands for net CO2 assimilation rate, the same as net photosynthetic rate. Ci represents the CO2 concentration in the intercellular air spaces. And A/Ci is just a shorthand, which means a plot of A versus Ci. So that's what ACi is. Why do we care what an ACi curve is? Why do we need them? The main purpose, as far as I'm concerned, is that they're essential in interpreting differences in photosynthesis, stomatal conductance, and Ci values. Just as an example, if we have 2 leaves, which have different A assimilation rates, different GS stomatal conductances, and different CIs, intercellular CO2 concentrations. So the question, and suppose that these measurements were made at the same light, CO2, humidity, and temperature. So we can ask the question, is stomatal conductance the only fundamental difference between these 2 leaves? Or is there something in the photosynthetic biochemistry that's different between those 2 leaves? So that's an important question. From the data, just simple A, GS, and CI values, there's no way of knowing whether there's any difference other than just in stomatal conductance that's causing the differences in assimilation rate and CI. So the way to answer that is to do an ACi curve. For leaf number 1, we have this blue dots. We are showing an A versus CI curve for leaf 1. We plot leaf 2 on that same curve. We see immediately that it is not on the same curve, which means that there is something with photosynthetic physiology that's different about leaf 2. It is not just a matter of differences in stomatal conductance. So that's one of the main purposes of ACi curves. The problem is that ACi curves differ depending on the light and temperature that you conduct them. This is just an example showing for all 3 of these species that light drastically affects the shape of the ACi curve. And you also see that temperature affects it, because These curves made at 35 Celsius are much more gradual increase at the top end and a much flatter top end of the curves at 20 degrees. So light and temperature both affect the shape of the ACi curve. So rather than doing multiple ACi curves under lots of different conditions, it's much easier to parameterize a photosynthesis model with an ACi curve than it is to create multiple ACi curves. So we use one A versus Ci curve to parameterize a model. And the model that everyone uses is a C3 biochemical model based on Farquhar, Van Kemmerer, and Berry. And then the model itself will then account for, once it's parameterized with an ACi curve data, then the model will account for variation in CO2 temperature and light. And this is just an example of that. This is an ACi curve analyzed using a utility, freely available Excel utility published by Sharkey that you can get access to from the PP Systems website. Has a link to that. You can see the actual data points. This utility actually takes A versus Ci data and converts it into A versus Cc data, where Cc is the CO2 concentration at the chloroplast. So you have the blue, which are the actual observations, and then these are fit into Rubisco limited parts of a curve, parts of the curve limited by RUBP regeneration, and the yellow one is limited by triose phosphate utilization. So those three parameters show up, as well as two more. So you actually, when you fit a steady state ACi curve, you get 5 parameters from Sharkey's utility. These are the maximum capacity for carboxylation by Rubisco, maximum electron transport rate, the rate of triose phosphate utilization, dark respiration, and mesophyll conductance. So you get 5 parameters from a ACi curve. Unfortunately, it takes a long time. It takes at least 30 minutes per leaf to get enough data to fit with the utility. So there's a faster way to do this now, and that is to utilize what's called high-speed CO2 ramping. You can see on this, this is just another A versus Ci curve. The orange symbols represent measurements made with a steady state system, taking 35 or 40 minutes to get those 10 data points. And all the blue data points were collected in 5 minutes with high-speed CO2 ramping. So it's a much quicker and gives you an equivalent result. So how do we do high-speed CO2 ramping? It's really 4 very simple steps, and I'll explain each step in a little more detail in a moment. Step 1 is perform what's called a stored differential balance function for the CO2 and water range to be covered by the measurements. Step 2 is to perform a CO2 ramping procedure with an empty cuvette. The third step is then perform a CO2 ramp with a leaf in the cuvette, and you can do multiple leaves. And just keep going all day long. And the 4th step is post-processing the data, which in the case of this instrument is very easy to do. So a little bit more about these steps. There's a stored differential balance on the CIRUS 3, which stores the information about how the sensitivity of the instrument changes with background CO2 concentration and background water vapor concentration. And the usefulness of this is in the post-processing of the data. The stored differential balance you do once the instrument is warmed up. It's done with a closed leaf chamber, and it takes about 20 minutes to do this. the values you get are stable for the day. So you only have to do it once per day, first thing. And then you're ready to run ACi curves all day long. So that's the story. You can edit these ramping scripts in many different ways. This is one that's just designed for a typical C3 plant. Things you can control are the starting CO2 concentration, the final CO2 concentration, the water vapor percent of reference, temperature, light intensity. We run these ACi curves at high light intensity because the model can predict downward what it would be at a lower light intensity, but unless you have the high value for the high value, you can't predict what it would be at higher light unless you've already measured it there. So we always run these unless for a very specific purpose. In general, we run these starting at using a very high light intensity. And you can also, typical with Osiris, you can change the program in the spectrum if you're using the LEDs. So you enter these values up here in these boxes, and they fill in this huge table automatically for you. And then you're all set. Save that and run the script. The first measurement is to run one of those CO2 ramps with an empty cuvette. And then you just repeat under the same conditions with a leaf in the cuvette, and then you can do multiple leaves. You can post-processing the data. This is just an excerpt from the standard output Excel data file, and you can see in this case, this is with a leaf in the chamber, and you can see you get nonsense under the CI values, and actually the assimilation rates are ridiculous also. What we do is take the values at the same time step from the empty cuvette and just import them into a column in the spreadsheet, then subtract the empty from the apparent assimilation rates, and that gives you a real value of A for each step in CO2. Then you calculate from the real value of assimilation rate, then you go back and recalculate a real value of CI for each time step. And that's all there is. So that generates a table of real A versus real CI for that leaf. So the advantages of doing the high-speed CO2 ramping is you get many, many data points for analysis. It takes a total of 5 minutes per leaf for a complete CO2 curve. Our competitor is limited to, in their rate of CO2 ramping, to 100 parts per million per minute, whereas we can go more than twice that fast. So their curves take much longer to complete than ours do. Our post-processing in Excel is straightforward, very simple, whereas the other system actually provides you with R programs to do the data analysis. Another advantage of high-speed CO2 ramping is that during the ACi curves, the metal conductance, because it's going so, CO2, the curve is conducted very quickly, so metal conductance does not change with CO2 concentration because it has a fairly long lag in its response. And we have customizable scripts that are suitable both for C3 and C4 species. Obviously, the biochemical parameters you get from the data are different between C3 and C4, but the scripts are customizable to temperature and the endpoints and beginning points. Like to conclude with a few tips and tricks to make things go smoothly. Before you start performing CO2 ramps, you need to change out your desiccants and all the chemicals to make sure that everything is fresh. Make sure you have a new CO2 cartridge in. Let the Osiris 3 warm up for about half an hour. Do a stored differential balance calibration, which takes another 20 minutes or so. And only, as I said before, it needs to be done only once a day. Then before you run your ramps, you have to go to settings and make sure that the zero differential balance mode is set to use the auto zero stored differential balance. And then if you're doing multiple curves, every 25 minutes or so, but less than every 30 minutes, you should perform a manual zero, which will avoid the instrument's automatic setting interrupting your curve in the middle. So every 25 minutes or so, manually perform a zero balance, and then you can just continue on all day long. And with that, I will end and answer any questions.
We have a question from Tina Cotulius. I apologize if that's not correct. A question on the slide, what if you do see stomatoconductance fluctuations during the fast ACi curve?
I have never seen that happen. Stomatoconductance measurements, there'll be a little, very small fraction of variation from time to time, but I've never seen it change substantially during one of these curves, either in C3 or in C4 species. If it were to change significantly, it would potentially complicate the calculation of CI. But as I said, I have never seen that happen, and I've done hundreds of these things. So, there is, just sort of instrument variation. It might change by a couple %, but in terms of significant changes, I've never seen it happen.
Okay. From MK, will the Cyrus 3 remind me of an outstanding manual zero? I could probably take that, Jim.
No, it does not give you any warning when it's going to do its automatic zero. It happens every 30 minutes. So you can time it yourself, but the instrument will just interrupt whatever's going on and do it. So that's why you need to manually do it before that 30-minute time comes up.
Okay. What is the average minimum CO2 concentration the Cyrus 3 can reach?
I have never looked at that carefully. I would guess probably 10 or so, but we normally, when we run these, we let the leaf sit. We have an initial equilibration period where we let it sit at about 100 parts per million. And that's done very deliberately based on experience. If CO2 gets too low and you let it sit at very low CO2, Rubisco will actually deactivate. And then the curve doesn't mean anything to you. But 100 seems to be okay as a starting point. I can understand circumstances where you might want to go below that, but I would be very careful about letting it sit at low concentrations for much time before you run a curve. C4s, you can probably, I'm not even sure I remember what the starting concentration we used for the C4 for the initial equilibration. I'd have to look. It's probably a little bit lower because C4s are happier at low CO2. So we probably have it set something like 50, but I would not use 0 for either one.
Okay. If you change the cuvette temperature, VPD, humidity, or other settings, do you have to perform the stored diff bal again?
No, the stored diff val will cover all of, it accommodates, what it's looking at is it's storing adjustments to the analyzer output based on differences in CO2 and humidity. And it's independent of temperature because, it has to do with the analyzer, and the analyzer is thermostated independent of the leaf temperature that you're using. So, doing that is appropriate for any range of CO2 temperature and humidity.
Okay. But if I cut a leaf, can I make this same routine? Or would it be, I'm assuming they're meaning if it's intact or if it's just cut from the plant?
Yeah. I can't give a general answer. I've never tried it. I know that sometimes people get stable photosynthetic rates from cut leaves for several minutes. Whether, I don't have the experience to know whether 5 minutes is a reasonable amount of time for that to stay stable after you cut it. I would say, just do trial and error and just hold all the environment stable, cut a leaf and let it see if 5 minutes is the rate will stay stable for you. If that's reproducible, then the ramping shouldn't affect that, how stable it is.
In post-processing a rapid ACi curve, why do you need to remove the first few points?
Just because they're not reproducible, they're kind of unstable. And that's why it takes a few seconds for the ramping system to produce reproducible steps. So it's just noisy data, and it's just not worth bothering with.
For field measurements, what are the most important factors to consider in order to get good ACi curves?
Well, field measurements, one of the hard things is to make sure that the leaf that you're measuring has been in a stable environmental situation for several minutes. Like the wind doesn't blow and have it be shaded for a few minutes and off and on shade, that kind of thing. You have to make sure that your environmental temperature and humidity are not too much of a shock to the leaf compared to what it's been sitting in outdoors. So you need to either tailor your time of day that you do these or the environmental conditions in your ramp to match what you expect the field to be somewhat. So what you're trying to avoid is shocking the leaf by putting it into the cuvette in a very different environment.
A question from Vit Glosser. Is there a recommended range of air humidity for this method?
Well, I mostly am dealing with crop species that have high stomatal conductances, and to avoid condensation problems, I always run at less than 100% reference humidity. So the issue is really avoiding condensation. So that partly that's a matter of trial and error. Put a leaf in and see what, use an input humidity, say of 70%. Put the leaf in and see if it adds 30% and brings you back up to what the leaf is used to. So that's not just for the rapid ACi. That's for basically any measurement. The less change of environment you can produce on the leaf by putting it in the cuvette, the better off, the more stable the leaf will be.
From Jose Felix Alvarez, are there ACi results and time-consuming comparative with another systems and erga location?
I guess I'm not quite sure what's being asked. We have done a lot of comparisons of doing steady state ACi with high-speed ramping on the same leaf, and get very reproducible results out of it. It's just that the rapid high-speed ramping just gives you the results much quicker. And our system is quicker than our competitor's system, just because we can ramp at a higher CO2 rate of increase in CO2. So we get the curve done quicker than their competitors can do it.
From Faisal Falak, how do we know that our data is perfectly right?
Not quite sure what that means. When you import the empty CO2 ramp data into the data set that has the actual leaf in it, you have to line up the time points so that you know that that you're subtracting the empty cuvette value from the same timestamp as your leaf. And I think that's really the only thing to worry about, and that's very easy to do in the Excel because they're labeled.
Right. From Pat Prez, I understand that speed for increasing the CO2 is the equipment, but does the leaf need time for equilibration?
No, the response of assimilation rate to CO2 concentration is instantaneous, or essentially. In terms of our time scales, it is. So no, that's the reason we can do CO2 ramping is because the photosynthetic response to CO2 is instantaneous. So as long as we just subtract the empty cuvette value, then we're okay. You can't do that with a lot of variables, but CO2 you can.
Right. So from Augustina, in classical ACi curves, you have to make measurements at 400 ppm twice.
You often do.
Is it necessary?
Yeah, a lot of times one does go back and repeat values to make sure that they come back to the same value. And the reason that's an issue primarily is because in doing slow ACi curves, stomatal conductance is changing at each step in CO2. And that's the reason why you may not get to the same point when you come back to that same CO2 concentration, because stomatal conductance, the second time you do it, may not come back to the same point. But in our case, with the rapid ACi, stomatal conductance is not changing, so therefore there's no real need to repeat at each second measurement at the same concentration. So that's one of the advantages, is that it's done fast enough that you don't have to go back and repeat things because stomatal conductance has not changed.
Question from Nick Jan Bank. Does the rapid ACi curves make steady state ACi curve measurements unnecessary?
I think ideally the answer is yes, it does. I think we're still at a point where reviewers may want you to prove again that it really works. So it's probably at this point in the history of the thing, you may need to give them at least an example of having done a leaf both ways to show that you get comparable data. But within a couple of years, it'll become accepted that gives you correct values.
And a question from Augustina Gallo. How about CO2 effects on stomatal conductance?
CO2, CO2 effects on stomatal conductance are slow. Let me put it that way. They definitely are there under most conditions. Closing as CO2 goes up, opening as CO2 goes down. But there's often a substantial lag time before they respond at all to a change in CO2, and that lag time is often more than 5 minutes. So if you're interested in stomatal conductance responses to CO2, this is not the technique you want. You want to do really slow, steady state, and I would do it manually so that you can watch stomatal conductance come down and equilibrate before you record your data. There's no prediction of how long that's going to take. Every species will be different. So if that's what you're interested in, do it manually and watch the results to stabilize. But it takes forever. Doing those is an extremely painful experience.
So another question from Carlos. Can you do the ACi curve under low oxygen concentrations?
Yes. We have done lots of them at 2% oxygen, and it works just fine.
So we've got from Irene, the Sharkey parameterization was done with slow ACi curves.
Yes.
Is it also valid to use them with the rapid ACi curves?
Yes. Yes. Because the curves have the same shape, you get the same curve either way. So there's no reason that the parameters would be any different.
Thank you for attending this webinar. To learn more about rapid ACi curves or the popular CIRUS-free portable photosynthesis system, please visit ppsystems.com.